Good news, yeah. So this is where we were. DRAM versus SRAM. Once again, just to have a summary, DRAM, slower access because we have a capacitor, we have a higher density, lower cost. Annoying is that it requires refresh. This I didn't talk about. The manufacturing of DRAM is not the same as when we are manufacturing the processors. It is important that we build very good capacitors. We do tons of tricks. We dig trenches and, put the capacitor underneath the transistor. Or we have the transistor and we stack the capacitor on top using very exotic structures. And those things are not needed when you are doing normal processors. So usually DRAM technologies are separate than the processing technologies. The SRAMs are faster. There's not a poor capacitor, there's not the poor hippo jumping into the pool. There's already an active circuit which is driving it. The density is lower because we are using 6 transistors. That's why the cost is higher. There's no need for refresh, which is great. And the manufacturing is the same as what you use in the processors. So now let's come to, this was just supposed to refresh how we realize the memories. And we just have to understand what are our issues. And the most thing that will bother us is that we cannot make a fast memory also large. It's either a large memory that is slow, or it's a small memory that is fast. Well, life cannot be perfect, right? So this is what a modern system looks like. And so this is a 4-core processor. So this is one die. And these are, whatever is on this die is actually manufactured using SRAMs. And because DRAMs use a different technology because of their capacitors, these chips are manufactured using a specialized process that tries to make these arrays as compact as possible, tries to make the excess transistors as less leaky as possible and the capacitors as large as possible. So they are usually in a separate chip. Here in this case, they are even in a DIMM socket. But if you look inside here, a lot of this chip is actually memory. Now, here you have what we call a level 3 cache. This is shared among all these cores. Each core has its own level 2 cache. And then once you go inside each core, you see here also some very shiny looking parts. So these are also the internal level 1 caches separately, once for instructions, once for the data. And easily 60 to 80% of a modern chip is just a sequence of memories. And remember, our ideal was that we have 0 access time, infinite capacity, 0 cost, blah, blah, blah. Not going to happen, because the ideal memory's requirements clearly oppose each other. So bigger is slower, that we already discussed. Faster is more expensive, we cannot afford to do it. Remember, the DRAM used only 1 transistor, but was slow. If I wanted to be faster, it wasn't going to work with DRAM. It had to be SRAMs or registers. But guess what? I need more transistor for that. So it's more expensive per area. I cannot put so much bits, and we are paying more. The other problem is, if we want to somehow access a lot of bits in parallel, this is also more expensive. So remember, when we were going to the array structure, this is what we started sacrificing. We said, we have 1 million bits, we have 10 billion bits, we can access them only 32 bits at a time. Say, okay, if you want to access 512 of them, we have to do something else. So just to bring it out, why is bigger slower? It takes longer to find out where the location is. Faster is more expensive. You may need to use different technology, SRAM versus DRAM versus tape, etc. And higher bandwidth is more expensive, which means that you need to have in parallel more banks physically available. You have to have more ports, or you need to use higher frequency, or you need to go to a technology that allows you to switch faster, meaning a new technology. So if you look at the sizes, now let me just also have this thing. So these numbers are like numbers from 2011, so they are a bit old, but the trend didn't change. So, multiply this by a constant factor, you still get it. So SRAM, if you build it in 512 bytes, so this is something in the order of the register file here, you can get it under a nanosecond, so that could work at 2 gigahertz, 3 gigahertz, whatever. An SRAM in the kilobyte, megabyte range is going to work in nanoseconds. The moment you go to a DRAM, you can make memories in the gigabytes, and you will have on the order of 50, 80, 100 nanoseconds. And on a hard disk or on some non-volatile memories, you can go to terabytes. The problem is you have a lot of bytes. It just takes an awful long time to access the data. 10 milliseconds is like an eternity if you are running at 1 nanosecond or at 0.5 nanosecond. It's really, nano, micro, milli. Also, dollars and chip area, so faster is more expensive. So SRAM maybe $10 per megabyte, DRAM $1 per megabyte, hard disk $1 per gigabyte. As I said, the numbers easily scaled by a factor of 10 right now, but the ratio is still the same. It's not only these, it's not only hard disk, there are newer technologies, flash memory, phase change memory, MRAM, resistive RAM. These ones are active research, so this is in this part, in the physics, where we are trying to find newer ways of storing data, accessing data, and in the coming years, they will probably play a larger role. Now, we have this issue, and this issue happened actually at the beginning when we were making the processors. There are these guys who want to make the processors faster. They had the transistors, the technology was growing, and everything was working at the same speed. So you had your processor running at 8 megahertz. There were things. They went to the moon. And your memory was also able to respond within that time. But after a while, the technology kept improving and improving, and the processors went faster and faster and faster. At some point, people realized, I cannot make memory accesses faster. Or they realized, I can make it faster, but I cannot grow the size of it. And guess what? This was annoying. They realized that, hey, we have to do this thing because it's not scaling the same way. The processor cores are getting much faster than the memories are. At that point, somebody had a very smart idea, and they said, you know what? We can have a lot of memory. We cannot have all of it fast, but we can fake it. The processor doesn't have to know that it is talking to like one giant, very slow memory. We will take a small memory that's really fast, and when the processor asks for data, this small memory is going to respond. Looks like a good idea, no? Agreed? So I have this gigantic memory, big, 16 gigabytes, and the processor is talking to this small 16 kilobyte memory. Because it's small, I can make it very fast. It's expensive, but it's small, so I don't care that I make this fast. So memory, this wants an instruction, it says, you want this instruction, ta-da! And the guy takes it and says, oh, it's fast. And, you continue doing this. That's the idea. What's wrong here? What doesn't work, or what do you think is the main problem? Someone else? No? Yeah? Yeah, well, there was a reason why we had a big memory, right? I mean, we need this big memory. How do I decide what data goes into this small and fast memory? If I have a good way of knowing which data will be needed, I could, transparently maybe, either through software or automatically by hardware, bring the data from this very big, very slow memory. I can say, you know what, I think you are going to use this data. Ta-da! And then if this magically happens, then every time we are making a memory access, this thing will be magically there. So this is the idea that brings us to caching. So we have multiple levels of storage, progressively getting larger, and each one getting progressively slower. And we are trying to find ways, and it's very funny, it was very effective from the beginning. And then people realized, you know what, I don't need to care so much about the speed of the memory, as long as I can act as if I am a fast memory, the processor will not notice. And thus, the cache hierarchy was born. So this is what we want to do. We have everything what we want, we put in this big memory, and we have this like tiny but very fast memory attached to the processor. And whatever we want ends up in this fast memory. And it is possible to copy things back and forth. And I have the best of both worlds. So this big memory is cheaper per byte. And that small memory up there is faster per every byte. Now, they first started doing this with only one level. And then soon, you know, the discrepancy between the speed of one and the size of the other one grew so much that we ended up having a few ones in between. So we started calling the one at the very top, level 1, level 2, level 3, 4, 5, 6, 7, and then you end up with your big, slow main memory. And it's actually, if you think about it, when we go back to our processor, these load store architectures like the MIPS that we are studying have this register file, and you are only operating on the register file. It's as local, as small as it can get. You move all the data, you have a load instruction that loads the data here, then you execute quickly on this one, and then you store it back again. It's called the classical load store architecture. You load from a slower memory, you bring it close, you operate on it. Once you are done, you write it back. And this is, if you think about it, this is also part of that hierarchy. This is why it's also drawn here. So there is the CPU, there is a register file, which is already part of your instruction set architecture, already told about this. And then this guy is putting an address, and there is a cache, maybe more levels, and there's main memory. Maybe there is even some of the memories mirrored onto the hard disk, and the CPU doesn't know about it. It just issues an address and requests a data for it. Okay? So far? How do we do this magic? If we can get most of our accesses in this cache, we are golden. If we are not in this cache, then we have to spend some time in retrieving whatever data was needed, and we still have to pay the penalty. So if we have a perfect oracle, like a little guru that sits next to the program and says, I know, in the next few cycles, you're going to use this data. The way you are programming tells me that this is going to be next. You know? If you have like these magical super oracle, things would work well. We don't have an oracle usually, or not here, and we use two tricks. So the two tricks that we use are locality, and we have two ideas here. One of them is spatial locality, locality in space, and the other one is temporal locality. Locality in time. So let's go with it. So the temporal locality says, if you have just accessed some value in the memory, it's very likely that you are going to use it again. Remember that multiply add, so you have some value, you are adding and multiplying and adding to the same value. So if you access one memory location, let's keep it into the cache, because very, very likely you are going to access it again and again and again. And, well, this doesn't work for this class, right? Since you are here today, there's a good chance you will be here again and again, regularly. I will memorize you. Let's see how that works. Okay, spatial locality is if you access the data structure it's very likely that you are going to access the next location, next data location as well. It's very likely that you have an array. That array is distributed into consecutive memory addresses. So if you are accessing memory location, whatever, 0f00, it's very likely that the next time you access something, 0f04 and 0f08, 0f0c, whatever, will be next. So if I am bringing one data, don't only bring one data, bring all your friends, you know? Bring, I don't know, 8 words together, bring 16 words together. So these are the 2 tricks that we are using. And yeah. So these are the 2 tricks that we will use to make sure that data ends up in the cache, so that most of the data we are looking at will be in the fast memory. This is not perfect. Notice that, and we will go a little bit into details, how we are managing this data. It's not perfect. It cannot be perfect. It's not a perfect oracle. It's a good enough approximation, and you will see what kind of trade-offs we can make. And there will be some parameters, and they make excellent exam questions. You know, investigate the performance of a system which has the following memory hierarchy. Which one can execute this program faster? Makes always good exam questions. Now people woke up. Makes excellent exam questions. Okay. So this is the spatial locality and the things. So once again, nearby data in memory will be accessed in the near future. And the temporal locality is the ones that you once accessed will be used again and again. In your textbook, there is an analogy that actually works very well. It's about the bookshelf. So you can imagine your main memory as the library, the ETH library, where, you know, you want to read the book, you have to go to the library, you have to check it out, the nebis, and then, you know, there is this nice clerk, hands you over the book, then you have access to your book. But now you're studying, and there are a couple of books that you use regularly, so why go to the library every time you need a book? You say, I'm going to pick the books that I read most, and I'm going to put them on my desk. My desk is not very large. I may put 8 books here, and then I have a bookshelf a little bit further away in my room where I can put maybe another 40 books. And if I am studying the subject digital circuits, I'm going to have my favorite books here. Then I'm going to have the Dilbert comics here, etc., etc. And for everything else, I'll go to the library. Once I'm done with the digital circuits, I can collect these books, return them to the library, and bring in new books. Linear algebra, I don't know. That didn't even get a reaction. Okay. So the idea that we want to do is, we want to keep this memory working at the same rate as the processor. Why? Going back to our single cycle architecture, and know full well that single cycle architecture is a little bit like a toy example, but when we are here, this is a program counter. He puts the address and expects that the data, the instruction corresponding to this address is there within the same cycle. This means that it has to work as fast as the rest of the system here. This can only work if this memory is pretty small. Ergo, you want to make this level 1 cache tightly coupled to the processor so that they can work at the same speed. This is why the caches in modern processors are really built into the system inside the processor. And you would even have 2 separate caches, one for the data and one for the instruction, because the feeding instructions to your execution unit and providing your execution units with data are 2 independent locations. They have their own locality principles and work that way. Now, because you want to have this processor working fast and this cache matched to it, you cannot have a larger cache. So this is why you end up maybe having another hierarchy saying, okay, so this is maybe 16 kilobytes, And then I have a larger one, maybe 256 kilobytes, that is not as fast as this one, but still much faster than this one and not so bad. So if we are looking for data here, we cannot find it, maybe a copy of it is here. If not, I go one level up, etc., etc. You will, now comes the other question. How do we decide on the management of this data? So for your books, you know what you are doing, so you can do it either manually. The programmer is in charge of moving data. In programming terms, you would call this prefetching. You would know what data you are going to use. You call some functions, instructions, make sure that the data you're looking is loaded already into the cache before your main loop hits it. The other one is automatic. The hardware in the background manages this automatically without the programmer knowing about it. Now, both of them are being used. What you would most probably encounter is the automatic way, but there are increasingly architectures, GPUs, which do the movement of the data manually. It is a pain to do this. It's not very easy, especially if your programs do not have regularity, if they are not, some data parallel architectures, it becomes very difficult. But it is done in embedded processors and GPUs, where you call it a shared memory. Now, the automatic one is, what you would want. You say, hey, I just want to program this damn thing. I don't want to think about what's the cache, what's happening. Address, give me data. Remember the first slide that I was showing? This is the way you want to see the programmer. And the average programmer doesn't need to know about it. You don't need to know how big the cache is, how it works to write a correct program. This is what is happening. However, we are in a huge competition and we want to write better programs, and you will realize, tomorrow we are going to go a little bit more into the details. If you know a bit about what your system looks like, if you know the limits of your caches, the speeds and things like that, you can actually write programs that run much faster than someone who doesn't have any idea. So this is why this lecture and this particular lectures and the general lecture series is interesting. Giving you this insight will help you also become a better programmer, and help you develop faster applications. Now, you can read about the automatic management in memory hierarchy. It goes back a long time, 1965. Even I wasn't born then. And there are also some other older cache-related papers. So these references are all there. If you're interested, read them. Take some time. I mean, it's not like reading them will give you a higher grade. If you're interested in computer science, if you're interested in computers, these things are interesting. They will help you. Don't read all of them, but maybe every week, set aside half an hour, time yourself and say, let me read some papers about computer architectures, about computer algorithms. It will help you in your career to look at them, because most of the things we use today have the ideas were developed in those papers, and they are very pure and very simple. They are not filled with, gigabytes, this. The ideas are in there. So, modern memory hierarchy looks like this. So at the very, very top level, you have your register file. I still have my drawing here. So the register file, the compiler is actually the one that manages it. You can also write manual code. You may have 32 words, 64 words. Some larger GPUs have 128, 256 words that the compiler automatically maps your values to that. After that, you have your memory abstraction, and you have different levels of cache. These numbers are typical for today's computers. They may change a little bit, but the level 1 cache, the faster one, is maybe 16 to 64 kilobytes, runs in the nanoseconds, maybe not exactly at the same speed as the processor, but maybe every 2 cycles, 3 cycles. L2 cache is then larger, 512 to 1 megabyte. It runs substantially slower than L1. And then maybe you have L3, L4. The main memory is in the gigabytes, and the access speed there is hundreds of nanoseconds or 100 nanoseconds. And then you have your the memory that is then swapped onto your hard disk, which is painfully slow. I mean, this is an eternity for a program running on a processor that runs at multiple gigahertz. And it is now interesting to see how fast we can get. So this is the last part that I'm going to cover today. And for, we have multiple hierarchies, and for each hierarchy, let's say level I, you have the intrinsic access time, how fast you are able to read from this memory. We call this TI. And then the perceived access time is capital TI. The perceived access time is actually either you find it in this hierarchy. So if you are in level 2, there is a chance, which we probability, that we find the data we are looking for at this level of the memory hierarchy. So this probability is HI. We hit and we access it, and the access time is TI. If we miss, that's the other probability. Those probabilities will add together. So the hit probability plus miss probability is 1. So maybe 90% of the time we are hitting and we are accessing the memory within, let's say, 2 nanoseconds. 10% of the time we are missing, and now we pay the price. We have to go to the next level, and accessing the data at the next level has a longer access time. And by looking at our miss rates and hit rates, as well as the access times, I can calculate how much it will look like at this level of the memory hierarchy, how long it takes for me to access data on average. So if you write it actually, so this is the hit probability times the access speed plus the miss probability. We have to access it once because, how do we know we are missing? We try to access, it says, no, it's not here. Then we go to the next level and says, bring it. And then that guy takes some longer time and returns to you. If you do the little distribution here, you will realize that seemingly the access time will be the access time of this level of hierarchy plus the miss probability at this level times the access time of the next level. And this one obviously goes recursively because, so this is for T1, T2, T3, you can calculate it. And what you are interested in is to find an acceptable T1 with which you can operate. So at the first level of memory hierarchy, at the first level of your cache, you want to have it working well. So if you look at the formula, it's very simple. You have to keep the miss rate low. You have to keep the access low. How does this work? The miss rate, well, you have to make sure maybe that the capacity of your cache is big. So more likely you can put more values into your cache, and you are very likely to find the data that you're looking for. Now, the problem is, if you make the capacity larger, it might be that your memory becomes larger, and because your memory becomes larger, the access speed goes up. So, well, you have to find a balance there. You can lower the MI by a smarter cache management policy. You buy a better Oracle. You bring data better into the cache than another way. And there are smarter ways of doing it. We can anticipate what you will want to do. And how can I keep the next access low? Well, I can have faster lower hierarchy. So, a slightly faster level 2, a slightly faster level 3. I can have intermediate hierarchies as a compromise, or, well, I can use a better technology. I'm just going to give an example just to see how these numbers change. So these numbers are taken from real example. It's a fairly old design, 90 nanometer P4, Pentium 4, running at 3.6 gigahertz. The level 1 data cache is 16 kilobytes, and the T1, level 1 cache access is 4 cycles of integer or 9 cycles of floating point thing, so 4 cycles. Level 2 data cache is 1 megabyte, and the access is 18 cycles, and main memory is 50 nanoseconds or 180 cycles. Now, we are going to put some miss rates. So if the miss rate of 1, level 1 is 10%, and if the miss rate of 2 is 10%, you can make the calculation and you can say T1 is 7.6 cycles, T2 is 36 cycles, and you can calculate what it is. I'm just going to finish this example, that's the last slide. So if you can reduce the miss time, miss probability to 1%, all of a sudden you're almost twice as fast at the first level of cache. And the second level, 1%, we are almost twice as fast when seen from the outside world. If you say, okay, you know, I am not as fast here, but I am better here, you can come up with different compromises. Now, what determines the miss rate and hit rate? Well, this is your application running. So you need to do profiling, I mean, it's not like general. It depends on whatever program you are running here. So tomorrow we are going to look at how we organize the caches and how we have different types of caches and how we deal with these misses so that we can build better caches and understand the relationships a little bit better. Thanks very much.